And so with that, please join me in welcoming Sally Benson, Director of GCEP, and the GCEP Theme Leader for Carbon Capture, Use and Sequestration. She will kick off the symposium. Sally.
So thank you very much, Richard. And anyway, it's really great to see all of you here today. And I know there are many people in the audience who've been with GCEP from the very, very beginning. And so for those of you who traveled a long way to come here and help celebrate, thank you so much. We're looking forward to a wonderful event and getting back in touch with you. And then I know there are also some people here who are here for the first time, students, members of the community, faculty, staff. And for those of you who are just joining us for the first time, welcome. I hope you enjoyed the program as much as I'm looking forward to. So moving into my discussion, so what I want to do in the little bit of time I have with you is basically go through what have we done at GCEP, how have we evolved, and we'll start out with GCEP by the numbers. So we have a portfolio of research. That's the heart of GCEP, is the research we do here. And this pie chart shows an indication of the areas that we work in. And you'll notice right away that it's extremely broad. The different colors corresponds to different segments of the energy system: renewable energy, hydrogen energy, carbon-based energy systems, as well as all kinds of science and technology associated with electrocatalysis, batteries, and firming the grid, for example. The largest components of our program are in the area of solar photovoltaics, also in the area of bioenergy. We also have done a significant amount of work in advanced combustion, carbon capture and storage, and we have emerging areas such as in electrocatalysis that represent new ways to, for example, synthesize fuels. And I will talk more about all of that, but before that I'll just sort of go through the numbers. But very, very importantly is that our sponsors, ExxonMobil, Schlumberger, GE, Toyota, and now DuPont, make all of this possible. We wouldn't be here, we wouldn't be doing this research, we wouldn't have this collection of this community of researchers. So I really just want to take a moment to thank the sponsors for making all of this possible and having the vision that a set of major industrial companies could work together with Stanford University and so many universities around the world to help design and create an energy system for the future. Okay, so GCEP by the numbers, some key milestones and events. So in 2002, we launched this program with the sponsors and Stanford University, and you'll be hearing more about that, and we have some fun features that will bring you back to those times. In 2004, we had our first competitive solicitation for projects. So one thing that's important for everyone to know, at GCEP, the research we do is identified by faculty members at Stanford and other universities around the world. We then undergo a very rigorous peer review competition, and only the best of the best make it into our portfolio. And the first time we did this was in 2004. In 2005, we had the first GCEP Symposium, so we're now at number 8. In 2008, we had our first patent developed. In 2010, the first license of a GCEP technology. And in 2011, we were confronted with the challenge that taking a technology from a scientific idea to application is a very complex process involving figuring out how to manufacture it, how to finance it, how to scale it up. And so one of the small steps we took in this direction was to intentionally help support what we call follow-on research. And we were very pleased when last year the Bay Area Photovoltaic Consortium was established. This is funded about $25 million by the Department of Energy, a collaboration between Stanford and UC Berkeley that builds on many of the ideas. So one of the points I'm trying to make here also is that GCEP keeps evolving in response to opportunities and challenges that we see in the energy landscape. And then finally, 2011, DuPont joined us. We were all extremely happy and very appreciative that they gave the vote of confidence that, in fact, the GCEP model was a valuable and important one, and that they wanted to be a partner with all of us. So we thank them. Okay, some statistics. 5 sponsors. 165 faculty PIs have worked on GCEP over the years. About 60% of those are at Stanford University and 40% at other universities around the world. 713 graduate students and postdocs have received support for their work at this really crucial time in their development, where you get to explore new ideas in amazing depth and really create the foundation for your career in the future. 39 different research institutions, universities around the world. We have 80 projects that we've now invested in over the years. These are projects that typically involve multiple faculty members, students, postdocs, and they last for a period of 3 years, and they identify and tackle really tough challenges, but with the promise of something that would really make a difference in the energy system. 515 peer-reviewed publications. Everything that we do is open, and that's been a very important part of the ethic for this program, is that we would make things available through our website, through symposia such as this, and also through the traditional mechanism of peer-reviewed publications. Lots of conferences at presentations, 34 patents, and 4 startup companies are using ideas or technologies initiated through GCEP. So that's GCEP by the numbers. So now I just want to kind of give a little bit of examples of the evolution of some of our research portfolio in those major areas that I described. So I want to start first with the energy systems analysis. So you might say, well, you're a science and technology program. Why would you do energy systems analysis? Well, at the end of the day, the core group, the GCEP team, needs to be able to make good decisions about what to invest in. You know, identifying those areas which have the biggest potential for application at scale and have the biggest potential to reduce greenhouse gas emissions. So that's what we use energy systems analysis for. And we've had a number of iconic products. One of the first things we asked, if you want to provide energy to 9 billion people and you want to do it and protect the environmental system, the ecosystems, water, fresh air, and so forth, you need to really understand what are those big opportunities. So we did an exergy analysis of the global energy supply system. And the bottom line is really the big renewable resources are the sun and the wind. There are other ones as well, but they really are not that large in comparison to human energy demands. So our renewable portfolio focuses in large part on those technologies, or enabling technologies to make those a better contributor to the global energy system. Next thing we did is we said, well, how do we use energy? We work in the area of energy conversion devices. So you want to have energy conversion devices that we need to identify the important ones. And we did an analysis of the exergy flows throughout the global energy system, and also the associated carbon flows associated with those. So we were aware of where are the biggest opportunities in terms of the magnitude of the resource use and associated emissions. And basically the bottom line here is where we think we can have the biggest contribution is in the area of power and in the area of transportation. So moving on, so we're also thinking about new technologies, and you'd like to have a set of specifications for those technologies that, so at the end of the day, if they're successfully developed, you don't go, whoops, well, we're missing something. So we focused on really making very efficient energy conversion devices, and we focused on materials that were earth abundant and non-toxic, so that at the end of the day, we weren't reliant on things that would be scarce or difficult to dispose of. So as we pushed farther into that analysis, we said, well, what about other attributes? And we've done a study that basically shows that if you can reduce the energy, or the embodied energy, the energy needed to manufacture a device, such as a photovoltaic cell, it will allow you to increase the deployment and development of that energy conversion technology without impinging upon the global energy system. So low embodied energy. And then finally, we've taken a look at energy storage, and through a similar kind of assessment, identified that if you could make batteries with longer cycle life, instead of several thousand cycles that a battery could be charged or discharged, if you could increase that by an order of magnitude, that would significantly enhance the contribution that energy storage could make. So those are the kind of things that we study. So now let's try to apply some of those ideas, look at how we apply what we've learned about what would make a good contributor to a global energy system, and let's look at solar energy. So in the area of solar energy, our goal is high efficiency and low cost solar energy conversion. So where did we start and where have we come to? Well, early on, we became very interested in thin film technology. Silicon technology is much more mature, lots of companies already doing this. So we looked at some alternatives that could be efficient and lower cost and have lower energy requirements. So we started working on nanostructuring thin film photovoltaic devices. And then we said, well, if you wanted to have a very, very thin cell, that you need some way to enhance the amount of light that you could capture. And we started working on plasmonics to enhance absorption of the solar energy. At the same time, we'd like to capture a larger fraction of the incident solar energy. And in order to do that, we need to broaden the band gap over which we can collect photons. And we worked on silicon quantum dots in order to control the band gap. So all of those were about electricity, but what else could we do with solar energy? Wouldn't it be wonderful to directly be able to make other things, fuels from sunlight? So we started to work on artificial photosynthesis. So moving along, so the way GCEP works is we get proposals from faculty members, we go through this rigorous peer review and select projects, but then we step back, we look at our portfolio and we say, well, what's missing? So in about 2007, we said, well, what's really missing is really pushing the efficiency frontier for solar photovoltaics. What would happen if you could have solar cells that were greater than 45% efficient as compared to the best kind of cells, which might be in the mid-20s today? So we did a worldwide call for proposals in the area of solar energy and got the best scientists and engineers to identify their best ideas. And so we started working on ideas like hot carrier cells, thermal photovoltaic cells, and we even got some really out-of-the-box ideas that were sort of a hybrid between a photovoltaic and a solar thermal system. Basically, imagine if you had a photovoltaic, you could operate at very high temperatures and then capture the waste heat and run a steam cycle. So hybrid kind of energy conversion systems. And now, one of the things you'll see more about is an all-carbon solar cell. So thinking about earth-abundant, non-toxic materials, this would be a fantastic opportunity. So that's an example in the area of solar energy. Now I'd like to move on to the area of advanced combustion. Fossil fuels are the backbone of our energy system today and are expected to be the backbone for a long time to come. And there's an opportunity to significantly increase the energy efficiency of combustion processes and as a consequence, reduce CO2 emissions and also other kinds of air pollutants associated with the combustion of fossil fuels. So early on, we again did a very detailed study looking at what are the fundamental limitations to combustion efficiency, and need we be limited to things in the 30 to 40% range. And in fact, identified some design principles that would allow you to go to much, much higher efficiency, such as operating at very, very high compression ratios could, for example, give you an engine that achieved up to 60% efficiency or potentially even greater. And this morning we're going to hear from one of the ex-students who worked on this project and now has a startup to further develop these kind of ideas. Coal is really important. In China and India, the United States, we rely very heavily on coal. At the same time, we know that combustion of coal to produce electricity has very high emissions. So we asked the question, are there radically different ways that we could use coal that would simultaneously have higher efficiency and at the same time sequester those CO2 emissions not as a separate phase of CO2, but as, in fact, dissolved in liquids? And moving on to some recent work, taking advantage of combustion under extreme conditions with careful stoichiometric control that would result in a very high efficiency and essentially sootless diesel engine. Okay, so that's advanced combustion. So transportation, I mentioned power and transportation were two key areas where we think we can make a contribution. And our goal in the transportation area is efficient mobility options with low or no CO2 emission. So starting with some work in hydrogen, a big challenge is how do you store hydrogen safely with a sufficient energy density so that it's practical to put it on board a mobile device. And so we did early work looking at carbon nanotubes, and we're in fact able to show that it was possible to have a high density of hydrogen storage on carbon nanotubes. Also worked on advanced batteries, taking advantage of new discoveries in the area of nanoscience, nanotechnology that used, for example, silicon nanowires as part of a lithium-ion battery. The advantage being much higher energy density as well as improved cycle life. But what about if we could also think about making fuels? If we had electricity as an energy supply, if we have carbon dioxide, if we have water, wouldn't it be great if when we had excess power on the grid, for example, that we could use that to synthesize fuels? Well, if we're going to do that, we need to have a vastly improved set of catalysts in order to achieve this, and you'll be hearing more about this work. We also have a tutorial by Tom Jaramillo, one of our theme leaders, who will describe more about this. And then finally, sort of imagine an ultimate dream of having an electric car and driving down an electronic highway, and your car is charging. You know, you get in the lane, you get in the groove, and you're driving along, and your car is actually charging. So by the time you get to LA, you're not on empty, but in fact, you're full. So these are examples of our work in that area. Moving on now to bioenergy, another opportunity both in the transportation sector for transportation fuels as well as potentially in the power sector. And again, our goal is effective use of organisms for production of fuels and energy conversions. So looking back to some of the very early work, and you'll hear more about this, what about the idea of trying to intercede, and as you undergo photosynthesis and you're capturing that photon and generating electron, why not try to capture that at the very, very early stages? An alternative idea of looking at genetically manipulating bacteria to increase the amount of fatty acid production and basically precursors to diesel fuels, for example. Also very important, the competition or potential competition between food and energy crops is one that we really need to pay attention to. So the real opportunity is to move away from food crops as energy crops and rely on the cellulosic or the stalks and the roots and so forth of plants. But in order to do this, we have to become much more efficient with how we convert those materials in the plants. And lignin is really a huge challenge in terms of interfering with the ability to convert cellulose to sugars. So we've had a big effort on lignin. And this was one of the areas where we invited scientists from around the world to, again, give us our best ideas. We formed a team of 4 different research groups around the world to work on this problem. They've made amazing progress, and we'll hear about some of that today. What about the global potential of biomass? You know, we don't have unlimited lands. If we look at the total biomass resource, it's about 5 times global energy demand. So it's not that big. So if we want to use crops for energy, we need to be cognizant that we don't want to take lands that would be used to produce foods or provide other important ecosystem services. So just how much land would be available? And Chris Field, another one of the GCEP theme leaders, will talk to you about our results in that area. Other ideas, hydrogen for transportation, hydrogen for distributed generation. What about using microorganisms, or actually cell-free systems using enzymes from organisms to produce hydrogen from sugars? And then finally, some very exciting work also on producing methane. We take the natural synthetic capacity of microorganisms, communities of microorganisms to produce methane. When we provide them electricity, carbon dioxide, and water as a feedstock for that process. So a whole range of options. So moving on to carbon capture and storage, if we're going to reduce CO2 emissions in the near term or in the midterm from our fossil fuel combustion sources, we need to capture that carbon dioxide just like we capture and scrub many other flue gases. We need to take that carbon dioxide and isolate it from the environment. So this has been a bedrock piece of GCEP from the very beginning, working first on trying to store carbon dioxide in coal beds. Very little was known about this option. Also storing carbon dioxide in saline aquifers. What were the opportunities and challenges? At the same time, we began work in carbon capture. Our early work focused on membranes, and there was some very interesting work by our Japanese colleagues at Wright, who developed basically molecular gates for improving the effectiveness of membranes for CO2 capture. In the area of sequestration, again, all rocks are really variable, really heterogeneous, and so we needed to understand what the implications of the heterogeneity of underground rock formations would be on CO2 storage. But what about the idea, instead of storing carbon dioxide as a supercritical fluid or a gas, what about injecting it into locations underground where you could actually convert it to a mineral? We know in nature this happens. There are enormous deposits of magnesium carbonate, calcium carbonate. So we know it can happen. Well, how do we harness that chemistry and physics to make it work for us? Also, efforts in the area of monitoring. Monitoring is going to be crucial to effective implementation of CO2 storage projects, and we need to understand when we inject carbon dioxide into rocks, how does that change the rocks, and how would that inform how we monitor? And then finally, I mentioned that we have worldwide calls for proposals in certain areas where we don't notice gaps in our portfolio. We identified carbon capture as a gap in our portfolio, so we again had a worldwide call for proposals. 5 groups were selected to initiate research, and those activities are just going on, but we have a very an example of one of those would be biomimetic strategies that use carbonic anhydrase as a carbon capture technology. Okay, so just briefly, so if we're going to have more distributed, variable, renewable resources on the grid, we need to figure out a way to make them baseload electricity generation compatible with variable intermittent renewables. And key to making this work is the electric grid. And we identified this, again, as a strategic component of our portfolio. We identified a team of researchers who developed some really great ideas about flat controls and hierarchical information communication in order to improve grid reliability. And second, a really crucial issue is energy storage. Maybe we don't need it yet, but eventually we'll come to a time when energy storage becomes a crucial component of an electricity system with more renewables. So we're working on flywheels, solid oxide fuel batteries, reversible systems of that nature, and also battery technologies that are ideally suited to the grid. They may have low power, they may have low energy density, but have the appropriate power density and can provide those needed services to help balance the grid. Okay, so that brings us now to the end of my GCEP 10 years and about 20 minutes. And at this point, I would like to move on and briefly say what some of the things we're going to do at this symposium. So why do we have it? Basically, we have an amazing group of people in the audience, people from all different components of the energy system, from people working on manufacturing energy conversion devices to researchers working at the very, very early stages of fundamental science. And this provides a unique forum for us all to get together and share our knowledge and issues. And crucially is also to cultivate this ecosystem, to break down these communication barriers so that together we can quickly move these ideas from inception to application and opportunity, industrial opportunity. So briefly, we typically start and end the symposium with some plenary presentations. I'm really delighted today. We have Thomas Johansson, who will be talking about the global energy assessment, which I'll say more about in a minute. We have Ajit Sapre from the Group Vice President of Research and Technology for Reliance Industries. He's talking about his perspective on the energy landscape. Kathy Zoe will come and talk about the energy innovation ecosystem, which is alive and well in Silicon Valley. And finally, Doug Musica will talk about his perspective on energy research and decreasing reliance on fossil fuels. We'll also go back to the origins of GCEP. We'll have a fireside chat with some of the founders. We'll talk about the first 10 years through the perspective of people who are intimately involved with that. And then with luck, President Hennessy will also come and talk to us about what it's meant to Stanford. However, there was a Nobel Prize announced this morning, and he might be busy. So anyway, we'll see. But very exciting for Stanford. And the heart of the program are technical talks. We'll review research in carbon-based systems, bioenergy, solar energy, and advanced energy transformations and storage. So there'll be sessions on that. And so for those of you who've been here many times in the past, you know those can be kind of heavy lifting. You know, if you're not an expert in biofuels, it might be kind of impenetrable. So we have a new offering. We actually started this 2 years ago. We have tutorials. And the purpose of these tutorials, it's sort of an alternate to the main section, is to get to spend an hour and a half with one of the world's leaders in these technologies, ask questions, learn the basic vocabulary, learn what the critical issues are. So this year we've got 4 great tutorials. Dean Pam Matson will talk about Energy and Earth Systems 101. And Tom Jaramillo, again, our theme leader, Electrocatalysis 101. Ken Caldera from the Carnegie Institute will provide a geoengineering 101 tutorial. And then finally, our own Chris Edwards, the Exergy King. I don't know if he's here. He probably doesn't like that term. But he will spend an hour. We've heard so much about Exergy over the years. He will give us his version and a tutorial on Exergy. So students are also, really, GCEP is all about the students. That's who does most of the work, and postdocs. So we have a number of fun events. We have our student distinguished lecturers. Those were a huge hit last year. Really looking forward to those. Poster session, reception. I encourage all of you to come to the poster session. We'll hear from our 2 postdocs. And we have a student-sponsored networking lunch. It's an organized activity. Maxine Lim has been working on that, and also a student social that is hosted by our GCEP student representatives. And then finally, we're going to wrap up with a panel talking about the future. So we'll talk a lot about the past 10 years, and the purpose of this last segment is to look into the future. What are the challenges and opportunities? And with that, I would like to end my remarks and move on with the rest of the program. So thank you. Thank you so much for being here. It's wonderful to see the room full. Thank you.